Good morning, everyone. My name is Seema Aarella. I am a PhD student in the Department of Computer Science and Engineering at University of North Texas, Denton, USA. I'll be presenting my paper, iPUF, a novel security by design paradigm to mitigate data manipulation and external attacks in cyber-physical systems. The outline of my talk will include introduction, a discussion on PUF-based security by design, challenges of PUF, the problem statement, the novel contributions of the current research, the proposed framework with the experimental setup and analysis of the results, and conclude with the conclusions of the research and future directions. Coming to the introduction, we know that cyber-physical systems are the backbone of modern IoT applications, which comes with a lot of security vulnerabilities depending on the type of security system that has been employed. For example, there is an increase in data manipulation and false data injection attacks that can simultaneously target multiple cyber-physical components, which will be larger security vulnerability. And as we know, physical unclonable functions which leverage the fabrication variations to generate secret key or unique key that is largely used for device authentication and identification is employed as a hardware security primitive in a lot of cyber physical systems. And despite their uniqueness, puffs can be manipulated by external attacks or glitches, which will cause errors in the response of the puff. So in order to mitigate these attacks and in order to ensure safe and reliable operation of the puffs, machine learning can be explored into providing solutions for these bit flips or errors in the puff responses. So that is the focus of this research. Coming to the security challenges, let's look at some of the attack vectors in the IoT domain and what would be the probable solutions to address these attacks. For example, at the threat levels, if you consider malware or integrity violation and fault injection or the glitching attacks, usually they can cause the system to distort or disrupt. So either the device will fail or the entire system will fail under these attacks. Some of the mitigation strategies for these attacks are hardware-assisted mitigation, using of trusted platform or a security-aware design. Coming to PUF-based security by design, considering that using hardware-assisted security or a security-aware design, a lot of these attacks can be mitigated. Let's consider that an IoT environment which is working on PUF-based security primitive, and at the edge layer we have all the PUF enabled IoT devices, and at the edge infrastructure where the data centers are also employing PUFs for say secure authentication of edge data centers or identification of the devices. So we have a complete ecosystem which is using PUF as a security primitive, and then the reliability of the PUF becomes paramount in these kind of environment in order to maintain the integrity of the security system. What are the challenges of using PUF? So PUF comes with its own challenge, like if we are employing PUFs, there is a need for generating unique responses each time. There is a need for maintaining the stability of the PUF responses. That is, over the time, for a given challenge, we always generate the same unique response. Then reliability of the PUF, that the responses or the operation of the PUF doesn't change over the time. And there is a need for always generating strong PUFs, which are again very essential for security applications. And other challenges include that it should be resistant to environmental variations, resistant to attacks, and usually PUFs comes with error correction methods. So the response that is generated from a PUF need to be error corrected in case there are some variations. Usually it comes with the normal PUF error correcting features are that they add additional circuitry for error correcting or use helper data that can reconstruct the original PUF response. But these solutions will add to the area overhead or to the computation overhead. So these are not feasible for applying at the edge if we are considering resource constrained edge. And also we have to focus on power consumption, that the error correction module should not be so extensive that it consumes a lot of power or a lot of computation power as well. Coming to machine learning solutions. So in this research, we are going to propose a novel machine learning based solution in order to predict these bit flips or erroneous response in the puffs that can happen due to either if the puff device is attacked or if the circuitry is glitched to produce a different response compared to the normal response. Here are some of the related research work which employs fuzzy extractors or fault injection modules in order to test the attack resistance of the puff, and fuzzy extractors to increase the puff reliability. Some of these methods are employed for error correction or to mitigate the external attacks on the puffs, but the drawback is that they add to the area overhead or to the computation overhead. The focus of this research is to approach at the solution which is going to be more suitable for edge processing, which doesn't add to the area overhead or to the computation overhead. The problem statement here is that puffs are vulnerable to external attacks and environmental variations. So environmental variations means any increase in the temperature around the puff or due to electromagnetic activity or seismic activity. These kind of environmental variations, rising temperature or falling temperature, will affect the puff performance, where it will not give the optimum or the required response. So there should be a strategy in order to mitigate these changes in the puff response due to environmental factors or external attacks. So this changes in puff response can cause the device failure or the complete security system failure. And in order to mitigate this, if you are going with traditional error correction modules, it is going to add to the area overhead, which is not suitable for edge processing. And the need for low power consuming and computationally inexpensive solutions is required in order to make a suitable error correction module for the edge computing or the edge devices. Now, contributions of this research include exploring machine learning as a lightweight solution in order to address this puff error correcting problem. And in this research, we are applying generative adversarial networks for detecting errors in the puff responses, which requires puff response data preparation, analysis and pre-processing, data organization and data set generation in a way that can be employed for GANs, and fine-tuning of GAN to handle binary data. So puff responses here considered are binary data sequence. So how we are going to visualize this binary data and then how we are going to train the GAN models on a binary data is a challenge in itself, because traditionally GANs are largely used on domains like image synthesis, and then generating an synthetic glitch data in order to develop and train our GAN on attack pattern recognition. This is the proposed iPUF framework, where the response data, that is the unique responses from a physical puff device, is gathered and collected in a way that is suitable for training the GAN after a lot of pre-processing. And the GAN tool is trained, and the feature that we selected that could be valuable in differentiating the real data from the fake data is the threshold value. So this module will assign a threshold value, a value which will separate the fake data from the real data. So any values beyond this will be labeled as either real or fake. So we are considering the threshold value as the value to detect the real data from the fake data, and once the fake data or the glitched data is detected, it can be sent to the mitigation system, where it will handle how the device or the system will proceed further. Upon detecting an threat or an attack, will it be corrected and proceed if there is no external manipulation is detected, or if the errors are genuinely because of some variations in environment. So there are two things. If it is a genuine attack, the system has to be removed from the connected environment. And then if it is not because of any external attacks and there is a flip or an error just due to environmental variation, then the system needs to correct itself and continue working. So these are the two things involved here in the mitigation. Coming to the experimental setup, we have used a 64-bit arbiter PUF architecture, which is implemented on an BSS3 FPGA. The performance of this arbiter PUF is tested with 49% uniqueness, 86% randomness, and 45% inter-HD, that is hamming distance, which are closer to the ideal values. And the data set that has been generated to train this model is, we have used 100K responses from 1000 challenges, that each challenge is repeated 100 times and the 100 responses are recorded for each challenge, making it a 100K response dataset. And this dataset, 80% is used for training and 20% for testing. Here is a visual representation of the distribution of real and the fake response data in the dataset. Some of the responses we have included synthetic glitches, which will be labeled as the fake data in order to train our model. Here is the training process. This is the control flow of the training process. The parameters are initialized and data is prepared, converting the binary sequences into strings. That is how the model handles the binary data. And helper functions are added, noise is added, and then generator and the discriminator are built. We are using the leaky ReLU in order to add more non-linearity into the neural networks. And then we are adding the sigmoid activation to the output layer. Then also we are adding the gradient penalty as tuning parameters to avoid over regularizing of the discriminator. After all these functions are applied and the model is trained, using the model is trained. Once the model is trained, this is the same algorithm representing the process of model training, adding the different fine-tuning parameters and activation functions. And once the model is trained, it is able to properly discriminate between the real and the fake data. So this result shows the distribution of discriminator output, where the discriminator is more confident in discriminating the fake data, and the confusion matrix showing the number of real and fake labels that has been identified by the model. So the results and the analysis shows that we achieve area under the curve of 99%, and the discriminator loss and the generator loss graph shows that over the time how both the discriminator and generator are stabilizing. Here are the prediction results. So based on the threshold value, we can see the discriminator score given to each data type. So the real and the fake data, that is the data with glitches or errors, has a different discriminator score. That is the threshold value based on which the results are predicted accurately. So coming to the comparison of results, this version using generative adversarial network shows 99% accuracy in predicting the real and fake data. Coming to the conclusion, this model utilizes advanced techniques like gradient penalty, noise regularization, feature matching, etc., tailored for binary data, and it enhances the training stability and improves the generator's capacity. to mimic the true data distribution. And the threshold value enables better predictions, and this can be used in form of a feedback-based system that can dynamically update the threshold values to adapt to diverse data inputs. For the future directions, this kind of a model can be tested in real-world conditions, and to predict dynamic features like voltage and current variations. Then more advanced complex GAN architectures can be utilized, and additional regularization methods can be implemented to narrow the confidence gap between the generator and discriminator. We can optimize this model for deployment on low power edge devices, and the use of this kind of study on binary data, GANs, employing GANs on binary data, will be crucial in developing deepfake image detection systems as well in the future. This is my presentation. Thank you very much.